Hello everybody, this is Navarrete, and today I'll be going over the stoichiometry with gases homework. So, let's get started. For number 1, it says consider the following reaction, and we have mercuric oxide decomposing into mercury and oxygen gas. It asks what volume of oxygen gas can be formed from 100 grams of mercuric oxide at standard temperature and pressure. First thing I'm going to do, looking at my equation, I need to balance it. So after checking and seeing how much of each one I have, I'm able to get these coefficients. So it tells me that for every 2 mercuric oxide that I have, it'll decompose into 2 mercury and 1 oxygen gas. Now that I have my balanced equation, well, I'm told that I have 100 grams of mercuric oxide. Let's change that to moles. So what I'm going to do first is write down what I have, 100.0 grams of mercuric oxide, and then I'm going to convert to moles. So in order to do that, I look at the molar mass, and it tells me that 1 mole of mercuric oxide has 216.59 grams. But I can do another step here. If I look at my balanced equation, that gives me a mole ratio. So I can go from moles of mercuric oxide into moles of oxygen gas. So what I can do then, and then just use my balanced equation and say, well, for every 2 moles of mercuric oxide, I'm going to get 1 mole of oxygen gas. And plugging all of that into my calculator, I'm able to see that I end up with 0.2309 moles of oxygen gas. We have moles, but we need to find volume. And luckily, we have an equation that lets us calculate that. If we use our ideal gas law, PV is equal to nRT, we can solve for our volume. Our volume would be our number of moles times our R constant times temperature divided by pressure. And we can plug everything that we have in. Our number of moles is 0.2309. My constant, since it's going to be in atmospheres, I'm going to say 0.0821. Temperature, since it's standard temperature, is 273 Kelvin. And my pressure is going to be 1.008 atmospheres. Plugging all of that into my calculator, I'm able to get a volume of 5.18 liters. Next up, it says, consider the following reaction. We have potassium chlorate decomposing into potassium chloride and oxygen gas. What mass of potassium chlorate is needed to make 5.00 liters of oxygen gas at standard temperature and pressure? Again, looking at my chemical reaction, there aren't any coefficients, so I'm going to balance it first. So you can double check your coefficients with mine. I get 2 potassium chlorate decomposes into 2 potassium chloride and 3 oxygen gas molecules. We want to know what mass of potassium chlorate, but we're given an initial volume. Using our gas laws, what we can do is if we have our volume, well, we can find our number of moles. So using my ideal gas law, I can solve for the number of moles at that specific volume. So plugging in what I have, since we're at standard temperature and pressure, I'm just going to use 0.0821 atmospheres per liter divided by mole Kelvin. My temperature is going to be 273 Kelvin. My pressure is going to be 1.00 atmospheres, and my volume is from the problem, 5.00 liters. Plugging all of that into my calculator, I get 4.48 moles of oxygen. I have moles of oxygen, but I need to go into grams of potassium chlorate. So, using my balanced chemical equation, I can convert from moles to moles and then from moles to grams. So, what I'm going to do is I start off with 4.48 moles of oxygen gas. And my balanced chemical equation tells me that for every 3 moles of oxygen gas that I have, that's going to come from 2 moles of potassium chlorate. Once I have moles of potassium chlorate, I can convert to grams of potassium chlorate using my molar mass. And it tells me that in 1 mole of potassium chlorate, it's going to have 122.55 grams of potassium chlorate. Plugging all of that into my calculator, I get 336 grams of potassium chlorate. Next, it says methane is burned according to the following equation. Methane plus oxygen will give us carbon dioxide and water. What volume of carbon dioxide at 745 torr and 24 degrees Celsius is collected by burning 25.00 grams of methane? Again, first thing I'm going to do, I see my chemical reaction. There aren't any coefficients, so I need to balance my equation first. Again, you can double check your coefficients with mine. I get 1 mole of methane and 2 moles of oxygen will combust into 1 mole of carbon dioxide and 2 moles of water. So looking at our problem, it says we start off with 25.00 grams of methane. Let's convert that into moles first. So I'm going to start off by writing 25.00 grams of methane. I'm going to need my molar mass to convert to moles. So that tells me that in 1 mole of methane, there are 16.05 grams of methane. I can then use my balanced chemical equation to go from moles of methane to moles of CO2. It tells me that in 1 mole of methane will be the same as 1 mole of carbon dioxide. Plugging that into my calculator, I'm able to get 1.558 moles of carbon dioxide. I'm in moles of carbon dioxide now. I need to find my volume. And luckily, we have our ideal gas law that lets us do that. PV is equal to nRT. I'm going to solve for volume. So just going to rearrange it a little bit. So volume is equal to nRT divided by my pressure. And then I'm going to plug everything in. Few changes to note here. My temperature is in Celsius, so I had to convert that into Kelvin. My pressure is in torr, so I had to use my R constant that is in torr. Once I plug all of that into my calculator, I'm able to get a volume of 38.76 liters. For 4, it asks, if 90.0 grams of water are decomposed into hydrogen gas and oxygen gas at 25 degrees Celsius and standard pressure, A, what will the volume of hydrogen be produced? I'm not given a chemical reaction, so I'm going to write my own. My water will decompose into hydrogen gas and oxygen gas. It doesn't have any coefficients, so I need to balance it first. I start off with 90.0 grams of water. I need to convert that to moles first. So, 90.0 grams of water. Using my molar mass, I'm going to convert into moles, and that tells me that 1 mole of water has 18.02 grams of water. Since now I'm in moles of water, I can go into moles of hydrogen gas. Looking at my balanced chemical equation, it tells me that for every 2 moles of water, it's going to make 2 moles of hydrogen gas. And now I can plug all of that into my calculator, and it tells me that I'm going to have 4.99 moles of hydrogen gas. I have moles, I know my pressure, my temperature, I got to change it to Kelvin first. I can solve for my volume. Using my ideal gas law and just rearranging it a little, I can plug all of the values that I have in already. 4.99 moles of hydrogen gas. I'm going to use 0.0821 since we're at standard pressure, which is in atmospheres. And I just converted 25 degrees Celsius into Kelvin. Plugging all of that into my calculator, I get 122 liters. For part B, it asks, what volume of oxygen will be produced? And you can go ahead and do all of the math and do all of the calculations very similar to part A. However, let's take a different approach to this. We saw that for 2 moles of hydrogen gas, it was 122 liters. And again, our balanced chemical equation is a mole ratio. So according to my balanced chemical equation, I'm going to have twice as many moles of hydrogen gas than I'm going to have of oxygen gas. Knowing that, I can say that my volume of hydrogen is going to be twice as much as it is going to be for my oxygen gas. So knowing that, I can say that my volume for oxygen is just going to be 61.0 liters. For 5, it says, ethane gas, C2H6, burns in air and produces carbon dioxide gas as well as water vapor. Assume all measurements are made at standard temperature and pressure. What volume of carbon dioxide is formed if 12.0 liters of ethane is burned? First thing I'm going to do, I don't have a chemical reaction, so I'm going to write one. Ethane burns in oxygen in air, and it will produce carbon dioxide and water. I don't have any coefficients, so I need to balance it first. Now that I have my balanced chemical equation, I can start solving. Instead of doing any calculations, I'm just going to use my mole ratios here. I'm told that I'm going to have 12.0 liters of ethane, and looking at that relationship between ethane and carbon dioxide is twice as much as ethane. So I can say the volume that I'm going to have of carbon dioxide is going to be 24.0 liters. For part B, it says how many moles of water were formed. We're given our volume of ethane, so let's solve for the number of moles. Using my ideal gas law, I can then rearrange it to find the number of moles. Plugging everything that we have in, we have our pressure, that's standard temperature and pressure. My volume was 12.0 liters. I'm going to use my R constant for atmospheres, and my temperature is 273 Kelvin. Plugging all of that into my calculator, I can get 0.535 moles of ethane. Looking at my balanced chemical equation, it says that for every 2 moles of ethane, I'm going to make 6 moles of water, which is 3 times as much. So I'm just going to multiply whatever I got here, 0.535, times 3. I'm going to end up with 1.61 moles of water. For part C, it says how many grams of oxygen gas will be needed. So let's convert from moles of ethane to moles of oxygen gas. I start off with 0.535 moles of ethane. My balanced chemical equation tells me that for every 2 moles of ethane, I'm going to need 7 moles of oxygen gas. And then using the molar mass of oxygen gas, I can convert to grams. 1 mole of oxygen gas will have 32.00 grams of oxygen gas. I can then plug all of this into my calculator, and it tells me that I'm going to need 59.9 grams of oxygen gas. For 6, it says ammonia gas is formed by the decomposition of ammonium chloride. Hydrochloric acid is the other product. A, write the equation for the chemical reaction. And looking at my problem, it tells me that ammonium chloride will decompose into ammonia and hydrochloric acid. Again, I don't have any coefficients, so I have to balance it on my own. And looking at it, it looks like it's already balanced. So while you don't have to add the ones, it might help you in the future. For B, it says, what volume of ammonia forms from 25.0 grams of ammonium chloride at standard temperature and pressure? So we start off with grams of ammonium chloride. Let's convert that to moles of ammonia. So we can start off by saying 25.0 grams of ammonium chloride. I know that in 1 mole of ammonium chloride, there are 53.50 grams of ammonium chloride. Looking at my balanced chemical equation, it tells me that for every 1 mole of ammonium chloride, I'm going to have 1 mole of ammonia. So I'm going to end up having 0.467 moles of ammonia. I have moles. I can find my volume using my ideal gas law. Rearranging my ideal gas law to find volume, I can plug everything that I have in already. My number of moles I just solved for. We're at standard temperature and pressure, so I'm going to use my R constant for atmospheres. Temperature is going to be 273 Kelvin, and my pressure is 1.00 atmospheres. And that gives me a volume of 10.5 liters. For C, it says, what volume of hydrochloric acid forms from 25.0 grams of ammonium chloride at standard temperature and pressure? I'm going to follow the same steps as we did for part B. So first I'm going to convert from my grams of ammonium chloride. I'm going to use my molar mass to convert to moles of ammonium chloride. And then I'm going to use my balanced chemical equation to convert into moles of hydrochloric acid. And that's going to give me 0.467 moles of hydrochloric acid. Again, we're given our moles. Using our ideal gas law, we can find our volume. Plugging everything that we have, we are told that we're at standard temperature and pressure. So my temperature is going to be 273 Kelvin. My pressure is going to be 1.00 atmospheres. And the moles is what I just calculated. Plugging that into my calculator, I get 10.5 liters. D asks, well, why are the answers for B and C what they are? And if you notice, we got the same answer for part B and part C. Why is that? Because of our mole ratios. Our balanced chemical equation tells us how many moles of each reactant and product we have. If we know the volume of one, then we can just use our ratios to predict the volume our reactant or our product will have. You don't always have to use all of these long equations. Use your ratios to help save you some time. Lastly, it says how many grams of ammonium chloride are needed to make 15.0 liters of ammonia at 27 degrees Celsius and 0.950 atmospheres. So we're given our initial volume, our temperature, and our pressure. Let's find our number of moles. Using my ideal gas law with some rearrangement, I can solve for the number of moles. Plugging everything that I have in, well, my pressure was given, my volume was also given. I'm going to choose an R that matches the units that I already have. The only thing that I needed to change was my temperature from degrees Celsius into Kelvin. Once I plug all of that into my calculator, I'm able to get 0.579 moles of ammonia. Now that I have moles of ammonia, let's solve for the grams of ammonium chloride. First thing I'm going to do is I need to convert my moles of ammonia into moles of ammonium chloride. And I can use my balanced chemical equation to create this ratio. After that, I can convert my moles of ammonium chloride to grams of ammonium chloride using my molar mass. And then I can just plug all of this into my calculator and get 31.0 grams of ammonium chloride are needed. And that's it. If you have any questions, don't forget to message me or Mr. Morgan on Schoology. But other than that, stay safe, and I'll catch y'all next time.